Okay, so next we have to learn 10 special type of matrices, but before that we will learn transpose of a matrix. So the definition of transpose is a matrix obtained by interchanging rows and columns is called transpose of a matrix. So this is a very basic concept. Suppose if I have a matrix A, the first row is 1, 2, 3 and the second row is 2, 3, 1. This is a matrix of order 2 into 3. It has 2 rows and 3 columns. Now if I want to calculate A transpose, then we can simply change its rows into columns. So A transpose will be a matrix in which the first row of matrix A will become first column of A transpose. So the first row is 1, 2, 3. So our first column for A transpose will be 1, 2, 3. Second row is 2, 3, 1. So this will become second column 2, 3, 1. And the order of this matrix, this will be 3 into 2. So a matrix obtained by simply changing the rows into columns or columns into rows is called transpose of a matrix. Now there are certain properties of transpose that you should know. Total there are 5 properties. The first one is, if you take transpose of a matrix twice, okay, if I have this matrix A, now this is A transpose. Now if you take the transpose of this matrix again, so you have to change the rows into columns. So again you will get this matrix A. So this is first property. If you take transpose twice, then you will get matrix A. Now the second property is that suppose if I have some number, say K is some constant and A is some matrix, then K into A, transpose of this matrix will be, you can take K outside, transpose of A. So this will be, this is our second property, K in transpose of K A transpose of this matrix K into A, this will be K into A transpose. The third property is, if I have two matrix A and B, then A plus B transpose, this you can write as A transpose plus B transpose. So this will be our third property. The fourth one is, if I have this is our third property, A plus B transpose, this will be A transpose plus B transpose. Then the fourth property is that if I have a matrix A and we have to find A transpose to the power n, okay, n is some number, for example 2, 3, some integer. So if I have to calculate A transpose to the power n, so I can write this as A to the power n transpose. We can take this index inside and transpose outside. So this is our fifth property. With the help of some examples, we'll see when to apply this formula. And the last property is reversal law of transpose. Reversal law of transpose. Now this reversal law is very, very important in case of transpose. We will see this reversal law in 3 places in this chapter. One here in transpose and other 2 in adjoint and inverse. So the reversal law of transpose is, suppose if I have 2 matrices A and B and you want to calculate the transpose of product of these 2 matrices. So this AB transpose will be nothing but B transpose into A transpose. So this property is called reversal law. AB transpose will be B transpose into A transpose. If you want to take transpose separately, then you have to change the order, and therefore it is called reversal law. You can extend this property for any number of matrices. Suppose if I have 3 matrices A, B, C, then I can write this ABC transpose as C transpose into B transpose into A transpose. So this property is called reversal law. So once we have understood the concept of transpose of a matrix, now we can discuss the different type of matrices. So the first matrix will be, total we have to discuss 10 type of matrices. So the first one is symmetric matrix. Now the definition of symmetric matrix is, all these 10 matrices are defined only for square matrices. So the first symmetric, the definition of the symmetric matrix is, a square matrix is called symmetric matrix. A square matrix is called symmetric matrix if A transpose is matrix A. If you take transpose of a matrix and you get the same matrix, then this matrix A is called symmetric matrix. Now obviously this is very basic definition. In order to check whether a matrix is symmetric or not, first you have to calculate the transpose. Then if you get the same matrix, then it will be symmetric. We are now going to see some properties of symmetric matrix, and we'll also see the second definition of symmetric matrix, with the help of which you can directly answer whether a matrix is symmetric or not. So suppose if I have a matrix A of order 3 into 3, I am taking example of 3 into 3 just to explain the concept. but this will be valid for any square matrix. So say this is my second row and this is my third row, 3 1, 3 2 and 3 3. Now if I take transpose of this matrix, then it means we have to change the rows into columns. So if this is my first row, then it will become first column, then second row will become second column, and the third row will become third column. So this matrix is A transpose. This is our matrix A. Now this is our A transpose. Now if A is symmetric, then it means these two matrices are same. If A is symmetric matrix, if A is symmetric, so this means matrix A and A transpose, these two are same. Now we know that in case of matrices, two matrices are equal when all their entries are equal. Now see what is happening. These diagonal entries are not changing. For matrix A, diagonal entries are A11, A22, A33. For A transpose also, these are the diagonal entries. So if you take transpose, then what will happen, that this element A12 will become A21, element A13 will become A31 and so on. So these elements will change their position. Now if matrix A is symmetric, this means these two are same. So this means element A12 has to be equal to A21, A13 has to be equal to A31. So in case of symmetric matrix, I can write that Aij is equal to Aji for all I and j. So this is very important property in case of symmetric matrix. The element Aij is equal to Aji. So if you want to write an example of symmetric matrix, you can write anything on diagonal because the diagonal entries are not changing. These elements A11, A22, A33 are the same place. So you can write any number on diagonal. But if this element is say 5, the element A12 is 5, then A21 has to be 5. If this element is 7, then you have to write 7 here. Here if you have 10, then this element has to be 10. So this matrix is symmetric. You don't have to calculate the transpose. Simply by seeing the matrix, you can tell that this matrix is symmetric matrix. The reason is Aij is equal to Aji, A12 is equal to A21, A13 is equal to A31, A23 is equal to A32. So in case of symmetric matrix, this you should remember this second definition, Aij is equal to Aji. Then in that case, you don't have to do any calculation. Simply by seeing the matrix, you can tell whether it is symmetric or not. So this is another definition of symmetric matrix. Now the second and very important point is the maximum number of distinct elements in a symmetric matrix. The maximum number of distinct elements in a symmetric matrix of order n is. Now see how many different elements are possible in case of a symmetric matrix. So if I have a 3 cross 3 matrix, then you can see that you can write any entries on the diagonal. So you can write different numbers on diagonal. So for n cross n matrix, there will be n diagonal entries and all those entries are different. Now out of remaining, if I have a matrix of order n, then it means total number of element will be n square. So off diagonal elements will be n square minus n, right? N is on the diagonal, total is n square, so n square minus n, these are the off diagonal elements, and only half of them are independent. Once you decide what you have to write above the diagonal, the element below the diagonal are fixed. So this means only half of them are independent. So this will be the formula for maximum number of distinct element. N on diagonal plus n square minus n, these are the off diagonal elements, half of them are independent. For example, here if you want to see how many different elements are there, so you have 3 different elements on diagonal. Total number of element is 3 square, 9. So off diagonal element will be 3 square minus 3 by 2, because you have to consider only the upper half or the lower half. Once you have decided the upper half, the lower half is fixed. So this means you will get 3 plus 9 minus 3, 6 by 2, 3. So you can see that total maximum 6 different element is possible, and this was obvious. 3 elements on diagonal and only these 3 are independent. Once you decide these three are already fixed. So these two results you have to remember in case of a symmetric matrix. The first one, Aij is equal to Aji. Once you know this result, you don't have to do You don't have to calculate the transpose. You can directly tell whether a matrix is symmetric or not. See, this matrix is called symmetric matrix because it is symmetric about the diagonal. If you take the image of these three elements, then you will get these three elements. So therefore this is called symmetric matrix. So this one is the first result, and second, the maximum number of distinct element. So in some book this formula is also simplified. You can take 2 as LCM, so you will get n square plus n by 2. But you should not remember the formula. You should know the concept that why this formula we are getting. N on diagonal plus n square minus n by 2 of diagonal elements. So after this we'll talk about a skew symmetric matrix. Okay, so our next type of matrix is skew symmetric matrix. Now the definition of a skew symmetric matrix is a square matrix is called a skew symmetric. A square matrix is called a skew symmetric matrix if A transpose is minus A. In case of symmetric matrix, we have seen that A transpose is equal to A. In case of skew symmetric, transpose of the matrix is negative of A. Now again, this is the definition of a skew symmetric matrix, but we will learn how to find directly by seeing a matrix that whether it is skew symmetric or not. So if this is our matrix A, then this will be our A transpose. The diagonal elements are same. Now if A is a skew symmetric, if A is a skew symmetric matrix, then we know that in case of a skew symmetric matrix, A transpose is minus A. So this means all these elements are negative of their corresponding elements in A. So I can write that this element A11 will be negative of this element A11. So A11, this will be negative of A11. This means A11 is 0. 2 times element in first row, first column is 0, which means A11 is 0. So in a similar manner, you can show that these elements are also 0, A22, A33. So this is first point in case of a skew symmetric matrix. The diagonal elements of a skew symmetric matrix are always 0. So the first point is, this we can write here, the diagonal elements of a skew symmetric matrix, the diagonal elements of a skew symmetric matrix is always 0. So this is the first point. And the second point is that in case of a skew symmetric matrix, now see, if A transpose is negative of A, so this means A21 is negative of A12. A31 is negative of A13. So we can write the second definition of a skew symmetric matrix, that Aij is negative of Aji. So this is the second definition of a skew symmetric matrix. In case of symmetric matrix, Aij was equal to Aji. In case of a skew symmetric matrix, Aij is negative of Aji. So if you want to write an example of a skew symmetric matrix, the first thing is you have to write 0 on diagonal. We have seen that diagonal elements of a skew symmetric matrix are always 0. So you have to write 0 on the diagonals. And if I have 2 here, then this element will be minus 2. A12 is negative of A21. If I have say 4 here, then this element will be minus 4. If I have 6 here, then this element will be minus 6. Aij is negative of Aji. So this is second important point related with a skew symmetric matrix. And the last point, which is obvious, is the sum of all elements in a skew symmetric matrix. Sum of all elements in a skew symmetric matrix is, now this you can directly see, diagonal elements are 0, Aij is negative of Aji. So if I add these two, I will get 0. If I add these two, again I will get 0. So if you add all these elements, then you will get always 0. So in case of a skew symmetric matrix, sum of all the elements is always 0. Now after this, we have to talk about some of the properties related with symmetric and a skew symmetric matrix. So till now we have discussed the properties separately. Now the next thing that we have to discuss is that properties of symmetric and skew symmetric. So the first point that we should know is that if A is symmetric matrix, if A is symmetric, then A transpose, A inverse, K into A, then if B is any matrix, then B transpose AB, A to the power n, all are symmetric matrices. So this is again a very important point. In case of symmetric matrix, if A is symmetric, then this transpose inverse matrix A multiplied by some number, or if B is any square matrix, then B into A into B and A to the power n, all are symmetric matrices. N is some positive integer. So this is the first point related with symmetric matrix. And in case of skew symmetric matrix, if A is skew symmetric, this implies A to the power n, this will be symmetric if n is even. This point is also very important. If A is a skew symmetric matrix, then A to the power n, this will be symmetric matrix if n is even number, and this will be a skew symmetric if n is odd. In case of symmetric matrix, you can see that A to the power n is always symmetric, whatever be the value of n. If A is symmetric, then it means A square. Okay, here this will mean that, here this thing will mean that if A is symmetric, this means A square, A cube, A to the power 4, all these are symmetric matrices. Any power of symmetric matrix is always symmetric. But in case of skew symmetric matrix, this A to the power n will be symmetric or skew symmetric depending on whether n is even or odd. For example, if A is skew symmetric, then it means A square, A to the power 4, A to the power 6, all these are symmetric matrices. All the even powers are symmetric, and all the odd powers, A cube, A to the power 5, A to the power 7, all these are skew symmetric matrices. And it is very easy to prove this result. See, if it is given that A is skew symmetric, then it means A transpose, this will be negative of A. If A is skew symmetric, then it means A transpose is negative of A. This information is known to us. Now we want to find whether this A to the power n is symmetric or skew symmetric. So calculate the transpose of this matrix, and if you get the same matrix, then it means it will be symmetric. If you get a minus sign, then it means it will be a skew symmetric. So A to the power n transpose, you can write this as A transpose to the power n. And since A is skew symmetric, A transpose will be minus A. So I can write this as minus A to the power n, and this will be minus 1 to the power n into A to the power n. Now there are two possible values of minus 1 to the power n. One possible value is 1 if n is even number. So I will get A to the power n if n is even. And this will be minus 1 to the power n, this will be minus 1 if n is odd. So I will get minus A to the power n if n is odd. So you can see that if I take the transpose of this matrix, then I will get the same matrix if n is even, and therefore this matrix will be symmetric matrix. But if n is odd number, then I will and I take the transpose of this matrix, then I will get A to the power n with minus sign. So when n is odd number, this matrix will be a skew symmetric. If n is even number, then it will be symmetric. So this is a very important point. In case of symmetric matrix, any power of matrix A is symmetric. In case of a skew symmetric matrix, only the even power is symmetric, all the odd power is skew symmetric. So this was second type of matrix. After this, we'll see some of the questions based on symmetric and skew symmetric matrix, and then we'll learn other type of matrices. Okay, so our first question on symmetric and skew symmetric matrix is, let A be any square matrix, then which of the following statement is correct? Now three statements are given. The first statement is A plus A transpose is symmetric. The second statement is A minus A transpose is skew symmetric. And the third statement is A into A transpose is symmetric. Now if I want to find whether a matrix is symmetric or not, calculate the transpose of this matrix. We have seen that if A transpose is A, this means the matrix is symmetric, and if A transpose is minus A, this means the matrix is skew symmetric. So if I want to find whether a matrix is symmetric or skew symmetric, then we have to find the transpose of the matrix. If I get matrix A, then it means the matrix will be symmetric. If I get minus A, then it means it will be a skew symmetric. So our first option is we have to check whether this A plus A transpose is symmetric or not. So if I calculate the transpose of this matrix, I will get A transpose plus transpose of A transpose. Now we have seen earlier that if I take transpose of a matrix twice, then we'll get the same matrix. So this will be A transpose plus A. Now matrix addition is commutative, so I can interchange this and I can write this as A plus A transpose. So you can see that we have taken the transpose of this matrix A plus A transpose and we have obtained the same matrix. So this means A plus A transpose is symmetric matrix. Since the transpose of A plus A transpose is the same matrix A plus A transpose, therefore A plus A transpose is symmetric. So our first statement is correct. A plus A transpose is symmetric. Now the second statement is we have to find whether this A minus A transpose is skew symmetric or not. So again we are going to calculate the transpose of this matrix. So if I calculate the transpose, I will get A transpose minus transpose of A transpose. So this will be A transpose minus, if I take transpose twice, then I will get the original matrix A. Now if I take minus sign common, then I will get A minus A transpose. So as you can see that we have taken the transpose of this matrix and we have obtained the same matrix with minus sign. So this means A minus A transpose is skew symmetric. So therefore the second statement is also correct. Since the transpose of this matrix is negative of this matrix, so this statement A minus A transpose is correct, is skew symmetric is correct. So the first two statements are correct. A plus A transpose is always symmetric. A minus A transpose is always skew symmetric. Now we have to find whether this A into A transpose is symmetric or not. So again we have to take the transpose of this matrix. So I have this matrix A plus A into A transpose and we want to find whether this is a skew symmetric or symmetric. So calculate the transpose of this matrix. Now in case of transpose we have seen the reversal law. The reversal law was that if I have two matrices A and B, then AB transpose is B transpose into A transpose. So similarly here also we have to apply the reversal law. One matrix is A, another matrix is A transpose. So if I have to take the transpose of this matrix, then I will get B transpose into A transpose. Okay, A, B transpose, so this will be B transpose into A transpose. Now if I take the transpose twice, then I will get the matrix A. So this will be A into A transpose. So again, as you can see that we have taken the transpose of this matrix and we have obtained same matrix. So this means A into A transpose is symmetric. So therefore the third statement is also correct. So all the three statements are correct. A plus A transpose is always symmetric. A minus A transpose is always skew symmetric, and A into A transpose is again symmetric. So this was a very simple question. If you want to find whether a matrix is symmetric or skew symmetric, calculate the transpose. If you get the same matrix, symmetric. If you get minus A, skew symmetric. Now the second problem is, this is directly formula based problem. We have seen the formula earlier. The question is the maximum number of distinct element. Distinct means different. So the maximum number of different elements in a symmetric matrix of order 12 into 12 is. So we have a square matrix whose order is 12 and we have to find how many different elements are possible. So the formula that we have seen earlier is the maximum number of distinct elements in a symmetric matrix. The maximum number of distinct element in a symmetric matrix, this was given by the formula n on diagonal, n square minus n off diagonal elements, and only half were independent. So this was the formula to calculate maximum number of distinct element. Now here in place of n we have 12. So this will be 12 plus 12 square minus 12 by 2. So this will be 144 minus 12. So 132, this divided by 2, so 61. So if you do the calculation, you will find that this will be 78. So maximum number of distinct element in a skew symmetric matrix of order 12, this will be 78. Okay, so our next question is, these two are very interesting problem. The first question is, let A be the set of all 3 cross 3 skew symmetric matrices. A skew symmetric means A transpose is minus A, whose entries are either 0 or 1 or minus 1. Now the question is, if there are exactly 3 0, 3 1 and 3 minus 1, then number of such matrices is. So we have to use 3 0, 3 1 and 3 minus 1, and then we have to see how many skew symmetric matrices are possible using these 9 elements, and the matrix is of order 3 into 3. So suppose if we have this matrix, say I have this matrix of order 3 into 3. So So if the matrix is of order 3 into 3 and it is a skew symmetric matrix, then we have seen that the leading diagonal entry of a skew symmetric matrix is always 0. So if I have to use exactly 3 0, then we have to place this 0 on diagonal. So I have to place 1 0 here, another 0 here, and another 0 here. For diagonal elements, we don't have any option. We have to place 0 on the diagonals only. Now the question is, in case of either symmetric or a skew symmetric matrix, once you decide this place, say element in first row, second column, then this place is already fixed. If I am placing 1 here, then I have to place -1 here. Similarly, suppose if I place -1 here, then I have to place 1 here. And if I place say 1 here, then I have to place -1 here. So this is an example of a skew symmetric matrix. All the leading entries are 0 and Aij is negative of Aji. So this is one example of a skew symmetric matrix. Now the question is, how many such skew symmetric matrices are possible which will have exactly 3 0, 3 1 and 3 -1. So see, here you have only 3 independent places. Okay, only these 3 places, either above the diagonal or below the diagonal, are independent. Once you decide these 3 places, then the other 3 places are already fixed. You have to place the negative of these numbers here. So you have 3 independent places, and for each place, how many options you have? So for each one of these 3 places, you have 2 options. On this place, either you can place 1 or -1, and that will decide your next place. So for all these 3 places, you have 2 options. Either you can place 1 or -1. Similarly, for this place also, you can place either 1 or -1, 1 or -1. So for each of the 3 places, you have 2 options each. And since this work is that we have to fill all these 3 places, so here we have to apply the multiplication theorem of permutation and combination. So if I multiply these 3 numbers, I will get 2 into 2 into 2, 8. So this means total 8 matrices are possible, which will have exactly 3 0, 3 1 and 3 -1. And if you want to write those matrices, those 8 matrices, then you can easily see what are those matrices. Suppose if I place 1 1 here, so these 3 elements are -1 -1 -1. So I'm going to write only these 3 elements of all our 8 matrices, and that will decide our matrix. So one possibility is that we can place 1 1 1 on these 3 places. Then another possibility is that we can have 1 1 -1. This will mean that these 2 entries are 1 and 1, and here we have -1. Similarly, we can interchange this -1 in 3 ways. So I will get 1 -1 1. Then we will have -1 1 and 1. So these are the first 4 matrices. Now our next matrix will be 1 -1 -1. Again, you can interchange this 1. So I will get -1 1 -1, and then -1 -1 plus 1, and finally -1 -1 -1. So these are the 8 matrices, 8 skew symmetric matrix, which will have exactly 3 0, 3 1 and 3 -1. Here I have written only these 3 elements because once we decide these 3 elements, our matrix is fixed. For example, if I want to write the corresponding matrix, say matrix corresponding to this entry, so I will have -1 here, 1 and 1, and then you have to write negative of those numbers here. So the correct answer for this question is 8. The total number of skew symmetric matrices will be 8. Now this was first question. The second question is, if X and Y be 2 skew symmetric matrices and Z is a symmetric matrix of same order, so this means all these 3 matrices are of same order, then which of the following is symmetric matrix? So it is given that X and Y are a skew symmetric matrix. This means X transpose is -X, Y transpose is -Y, X transpose, this will be -X, Y transpose, this will be -Y, and Z transpose, this will be Z. So this information is known to us. Now the question is, these 3 options are given. This is multiple correct type question, so 1 or more options are correct. Now we have to find that which of these 3 are skew symmetric matrices. So we have seen that we have to find which are symmetric matrices. So we have seen that if any matrix is symmetric, then any power of that matrix is symmetric. But if a matrix is skew symmetric, then only even power is symmetric. So if X is skew symmetric, this means x to the power 44, this will be x to the power 44, this will be a symmetric matrix, even power. And similarly, y to the power 44, this is also a symmetric matrix. So the sum of these two matrices, this is also symmetric. So x to the power 44 plus y to the power 44, this is symmetric matrix. Similarly, x to the power 21, this will be a skew symmetric. Y to the power 21, again a skew symmetric, odd power. So sum of these two matrices, this will be a skew symmetric. We have to find which are symmetric matrices. Now this matrix x to the power 21 plus y to the power 21 will be a skew symmetric. So option B is incorrect. Option A is symmetric matrix. Option B is a skew symmetric matrix. Now we have to check whether this option C is symmetric or skew symmetric. So if I want to find whether that matrix is symmetric or skew symmetric, we have to calculate the transpose of the matrix. So, and if I get the same matrix, then in that case the matrix will be symmetric. Otherwise it will be a skew symmetric. So in option C, we have to find whether this matrix is symmetric or skew symmetric. Y cube z4 minus z4 y cube. Now we are going to calculate the transpose of this matrix, and if I get the same matrix, then it will be symmetric. If I get the matrix with minus sign, then it will be a skew symmetric. So I can write this matrix as y cube z4 transpose minus z4 y cube transpose. We have two matrices A and B. You can consider this matrix as 1 and this is another matrix. So A minus B transpose, this will be A transpose minus B transpose. Now the next step is, next we have the product of these two matrices, so we have to apply the reversal law. So if I apply the reversal law of transpose, reversal law was AB transpose is B transpose into A transpose. So I can write this thing as z to the power 4 transpose y cube transpose minus again AB transpose, so this will be B transpose into A transpose. So z to the power 4 transpose. So this was the reversal law. Now in case of transpose, we have also seen this property that A to the power n transpose, this was A transpose to the power n. So we can take the transpose inside and power outside. So we can write this expression as z transpose raised to the power 4 y transpose cube minus y transpose cube into z transpose raised to the power 4. Now it was given that x and y are skew symmetric, so x transpose is minus x, y transpose is minus y, and z is symmetric, so z transpose is z. So we are going to do this substitution here. So in place of z transpose, I will get z to the power 4. In place of y transpose, I will get minus y cube minus, in place of y transpose, again I will get minus y. In place of z transpose, I will get z. So now minus y cube, so I can take this minus sign outside, so I'll get z to the power 4 y cube minus minus plus, so y cube z to the power 4. So now if I rearrange this, if I write this as first term, so I'll get y cube z4 minus z4 y cube. So you can see that this was our original matrix, y cube z4 minus z4 y cube. So we have taken the transpose of this matrix and we have obtained the same matrix. So this implies this matrix is symmetric matrix. If A transpose is A, then it means matrix A is symmetric. So option C is also symmetric matrix, and therefore this is correct. So for this question, the correct answer are option A and C. These two are symmetric matrices, while option B is a skew symmetric. So this was last problem on symmetric and skew symmetric matrix. After this, we'll talk about orthogonal matrix.